Good morning students. In today's video we are going to continue with the limit state of collapse for Flexure. In the previous video we have seen the stress block parameters, that is if you see we have taken one singly reinforced rectangular beam and we have found out this compressive force C, that is equal to 0.36 FCK B into XU. The next is tensile force, that is equal to 0.87 F of I into AST. So this is going to act at a distance of 0.42 XU. These things we had found out in the previous video. Next we will try to find out what is the depth of neutral axis. How to calculate the depth of the neutral axis? So depth of the neutral axis is nothing but this XU. XU, how to calculate this XU? So what we can do, if you want to calculate the depth of the neutral axis, we can take, we can equate this compressive force, that is equal to the tensile forces. So therefore total compressive force is how much? 0.36 FCK into B into XU. This is the total compressive force. Then next is total tensile force, that is 0.87 F of Y into AST, 0.87 F of Y into AST. So how do you calculate this tensile force? That is nothing but area into the stress. Area of steel is nothing but AST. Then next is tensile stresses is nothing but F of Y. F of Y we have. So we are multiplying factor of safety, that is factor of safety for steel is 1.15, that is 1 divided by 1.15 we have. So if you calculate 1 divided by 1.15, it will be 0.87. So therefore ultimately this will be 0.87 F of Y into AST. This is nothing but total tensile force. So we are going to equate total compressive force, that is equal to total tensile force. So that will be equal to 0.36 FCK into B into XU, this value, that is equal to 0.87 F of Y into AST. So this value. So therefore I want to calculate this XU. So therefore you cross multiply this. So therefore this will be 0.87 F of Y into AST divided by this value, that is 0.36 FCK into B. So with the help of this formula we can calculate the depth of the neutral axis, that is 0.87 F of Y into AST divided by 0.36 FCK into B. So this already they have given in the codebook also. At the end I will try to show you. Next is we will try to calculate what is the moment of resistance. So moment of resistance is nothing but capacity of a section to resist the moment. So what is the capacity of this rectangular section? How much moment it can resist? So how do we calculate? So with the help of this formula further what we are going to derive, based on that we will try to calculate what is the moment carrying capacity of the section. So already we have seen this moment. Then next is, so as to calculate the moment of resistance, what we do? We will try to calculate either due to this compressive force or due to the tensile force. So let us see this lever arm. Lever arm is nothing but distance between this compressive force and tensile force. This is compressive force we have, this is tensile force we have. Distance between these two forces, this is nothing but lever arm, that is Z. So how do we calculate Z now? Z is nothing but this total depth is D. Total depth is nothing but this is D. Next is already we have calculated this value in the previous video, that is 0.42 XU. So if you subtract this, remaining will be D minus of 0.42 XU. This distance between compressive force and tensile force, that is D minus of 0.42 XU. That is nothing but the lever arm Z. Then next we will try to calculate moment due to this force about this point, or moment due to this tensile force about this point. That is nothing but Mu is equal to compressive force into lever arm. Compressive force is this into lever arm is this. So therefore 0.36 FCK into B into XU is nothing but compressive force. Lever arm is this distance, that is D minus of 0.42 XU. This is due to the compressive force. Similarly, if you want to calculate due to tensile force, that will be equal to moment due to this force multiplied by distance, that is tension force into lever arm. So therefore it will be 0.87 F of I AST this is nothing but the force, multiplied by the distance, that is d minus of 0.42 xu. Either with the help of compressive force or tensile force, we can calculate the moment of resistance of a section. So already we have seen xu. Xu is nothing but 0.87 f of I into AST divided by 0.36 of B. Then next is we have seen Z, that is d minus of 0.42 xu. So what we will do, we will try to substitute this value of xu. The xu is nothing but this value. That is, we will substitute here 0.87 f of y, 0.87 f of I into AST divided by 0.36 fck into B. So d minus of 0.42 xu, this is same. Then next what we are going to get is, if we are going to simplify this, so that will be equal to d minus of f of I into AST divided by fck into B. F of I into AST divided by fck into B. So you are going to get this as the Z value. So therefore, moment of resistance, if due to this force, for example, 0.87 f of I into AST into this is nothing but lever arm Z. This is lever arm Z. 0.87 f of I into AST into lever arm is nothing but Z. So Z value is how much? This value, that is d minus of 0.5 f of I into AST divided by fck into B. So this value we will substitute instead of Z. Therefore this formula you are going to get, that is 0.87 f of y into AST. This is Z value, will substitute here, that is d minus of f of I into AST divided by fck into B. Further, if you are going to simplify, that is, I will take this d outside. So this will remain same, 0.87 f of I AST, 0.87 f of I AST, d if you bring it outside, then next d divided by d, it will be 1. Then next is f of I into AST divided by fck multiplied by B into D. This you will get. So with the help of, this is the value with the help of which you can calculate the moment of resistance of a section. Next is, we will try to calculate what is the maximum depth of neutral axis. Maximum depth of neutral axis, x is nothing but depth of the neutral axis. So we will write it as xu max, that is nothing but the maximum depth of the neutral axis. So now why this is required now? Why maximum depth of neutral axis is required? So as we have studied over reinforced section, under reinforced section and balanced section. If you see an over reinforced section, it is called as compression failure. Under reinforced failure, it is called as tensile failure. What happens is, if you want to avoid the over reinforced section, that means a compression failure if you want to avoid. Why? Because it is a brittle failure. So what we are going to do is that we are going to restrict the depth of the neutral axis. We are going to restrict the depth of the neutral axis. So if you are going to restrict the depth of the neutral axis, what happens is that before that concrete is going to reach its ultimate strain, so our steel has to reach maximum its yield stress before concrete fails. That means before concrete fails, our steel has to fail first. So how we are going to restrict the section? Based on the maximum depth of the neutral axis, based on this value. So if you are going to restrict this xu max, then our failure will not be brittle failure, our failure will be like tensile failure. So how to restrict this value? So what should be this value? How we should calculate? So that can be calculated based on this strain diagram. Already we have seen this strain diagram. So this is nothing but maximum strain in concrete, and this is nothing but the strain in the steel. So this D is nothing but the effective depth, and xu max is nothing but the maximum depth of the neutral axis. I want to calculate what should be the maximum depth of the neutral axis. So what we can do, we can apply similar triangles. That is, this is nothing but xu max divided by this total depth, that is D. So that is equal to, we are applying similar triangles, that is this xu max divided by that is equal to this 0.0035 divided by this is nothing but effective depth total D divided by this value plus this value, that is 0.0035. This is 0.0035 plus of this value, plus of this 0.87 f of I ES plus 0.002. this value. We have applied a similar triangles. So therefore further if you simplify xu max by d, that is equal to this 0.0035, then next you simplify this, that is 0.0055 plus this value, that is 0.87 f of y into es, where f of y is nothing but the yield stress and es is nothing but the modulus of elasticity of steel, which is always taken as 2 into 10 raised to 5 Newton per mm square. So only by changing the value of this f of y, we will come to know what is the maximum depth of the neutral axis, how much we can restrict. So you can see here now, we will take one example. We will take steel of grade Fi415. Fe415 will take, that is yield stress is equal to 415. So in the formula, in the previous formula, if we substitute xu max divided by d, that is equal to 0.0035 divided by 0.005 plus 0.87 f of y. So f of y is nothing but 415 will substitute divided by e, that is 2 into 10 raised to 5. So if you simplify this, you will get answer as 0.0479. So that is approximately equal to 0.48 xu max by d. So this is nothing but the maximum depth of the neutral axis, that is 0.048 for grade of Fe415. That is for, so that is being shown in the table now. For different grade of steel, what is the maximum depth of the neutral axis? So just now we have seen one example, that is for 415. So maximum depth of neutral axis is 0.48. Similarly, if you substitute 250 in this equation, so you will get answer as 0.53. The next, if you substitute 500, we will get answer as 0.46. Similarly, if you want, you can calculate. So what all values it is being shown here in this table, we are going to get these values. So this is nothing but the maximum depth of the neutral axis. So if it is going to exceed this, our failure will be a brittle failure or compression failure, so which we are avoiding. So therefore, if you want to have under reinforced section, we have to take care of this limitation. If you see the table IS code also, already they have given in the IS code also. If you refer, let me show you the IS code. They have given these values also. So you can see here in the IS code itself, they have given in the page number 70, that is the limiting value of the depth of the neutral axis for different grade of steel is for Fi 250, 415, 500, it is 0.53, 0.48, 0.46. So this already it is being given in the code book also, you need not remember. Then next is, we will try to calculate, now we have calculated the maximum depth of the neutral axis. Then next we will try to calculate what is the limiting moment of resistance, MU-LIM, that is moment of resistance. So for a limiting section, LIM, right? So what happens is that how much our section can carry the moment, what is the limiting moment, how much it can carry. So what we can do, already we have seen what is the maximum depth of the neutral axis. Based on that, what we will do? So based on that, what happens that the maximum value of the moment of resistance is also limited. So already we have seen the maximum depth of the neutral axis. Based on that itself, we will try to calculate what is the maximum moment of resistance. Instead of what you do, XU, we will take it as XU minimum. So therefore, these are the sections what we have. So MU-LIM, that is limiting moment, is equal to, already we have seen this, that is 0.36 FCK into B into XU, 0.36 FCK into B into XU. So now this is XU max. So we are going to take this XU max. So this is XU max. So D into this distance, into distance lever R, that is D minus of 0.42 XU. D minus 0.42 XU we have. So therefore what we'll do, we'll further try to simplify. So what we'll do, we'll divide this 0.36 FCK into B, we'll try to divide it by D. So therefore XU max by D will have. So same thing like here also, if you have this gets cancelled, this is 1 minus of 0.42 XU max by D. Then next is like we have multiplied and divided by D. So you can take this D outside. You can take this D outside. So we'll have that D. So therefore this will be equal to, multiply and divide means it will be d square. Why? Because we will be knowing why we are keeping in this term, that is xu max by d value we know already. Just now we have calculated. So therefore we are keeping in this way. So therefore it will be d square at the end. So therefore 0.36 FCK into B, 0.36 FCK into B into d square we have. So xu max by d and 1 minus 0.4 to xu max by d. So further if you simplify for different grades of steel. So now this is the limiting moment what we have. We will try to calculate for different grades. So what we will do, we will take one grade, that is we will take Fe415 and M20 grade. So for that if you substitute here in this case, that is 0.36 we have xu max by d. So this value for Fe415 already we have seen the previous table, it is 0.48. So that value will substitute as 0.48. Then next is 1 minus 0.42, again xu max by d we have. So that will substitute here 0.48. FCK BD square. FCK what we will do, we will try to, afterwards we will try to submit. First let us see only based on the different grade of steel, that is FCK BD square. So further if you simplify this term, so we are going to get it as 0.138. 0.138, this is FCK BD square, FCK BD square. So this we are going to get. So this is nothing but the limiting moment of resistance for Fe415 grade of steel. Fe415 grade of steel. So this you have to remember. Similarly, if you want to calculate for Fe500, so Fe500 if you calculate, you are going to get answer as 0.133 FCK BD square. So for Fe250 if you want to calculate, it is 0.148 FCK BD square. Only simple, very simple what we have is that, for example now for 415, this value has changed, xu by d. xu by d is how much? 0.48 we have taken. If you want to calculate for 500 now, for 500, so what we have to do, instead of this 0.48, you have to substitute 0.46. So instead of this, you will get 0.46. If you substitute, you will get answer as 0.133 FCK BD square. So what here we have got 133 FCK BD square we are going to get. So these are very important values which we have to remember. So we will try to calculate what is the limiting moment of resistance. So how much moment it can carry based on your maximum depth of the neutral axis. So most of time these values are being used. For different grade of steel, these are the values which we have to remember. So further if you want to simplify more, so if you take M20 grade of concrete, you can substitute M20 here, that is 20. So if you simplify, you'll get it as this 0.138 multiplied by 20. If you do, you'll get 2.76. This term is going to depend on the section BD square. So therefore 2.76 BD square. So instead of this 2.76, you can take it as Q limiting. So therefore it will be Q limiting of BD square. So it is going to vary based on the different grade of steel. Similarly, we can carry for different grade of steel as well as the different grade of concrete. So what you can do now, so previously we had taken M20 grade of concrete and steel was Fe415. So for that Q limiting value was 2.76. If you take M20 and 250, it will be 2.96. M20 and Fe500, it will be 2.76. Similarly, we can calculate for different grade of steel as well as for different grade of concrete. So here if you substitute these values, so you are going to get this Q limiting values. These are the Q limiting values what we are going to get. So simply directly if you want to use next time, what we can do for M20 grade and what you can say and Fe415 steel, directly you can take 2.76 BD square. If you want for 500, 2.66 BD square. Directly we can come to know what is the limiting moment of resistance, QLM. The next is percentage of steel for a singly reinforced section. What should be the percentage of steel for a singly reinforced section? So what we can do further, I will tell you regarding that. The next is we have restricted the depth of the neutral axis. So this is our section B into D, and these are the strain diagrams. These are the strain diagrams for balanced section, under reinforced section and over reinforced section, right? If we take a balanced section, XU is nothing but depth of the neutral axis, so that will be equal to XU max. XU will be equal to XU max. So what is the maximum depth of the neutral axis? That is the depth of the neutral axis. Then we can say that the section is balanced section. EC is nothing but the strain in the concrete, and ES is nothing but the epsilon S is nothing but the strain in the steel, that you can write it as ES epsilon SU. Then next is, so this type of section you can call it as a balanced section. For example, if we are going to have under reinforced section, that means the steel what we are going to place, if it is less, then what happens is that this, you can see, this is the neutral axis for a balanced section. So this neutral axis, what happens is that it is going to shift upwards. You can see here, this is the actual neutral axis for a balanced section. So in the under reinforced section, what happens is the neutral axis, it is going to shift upwards. Now this is the neutral axis now. So this has shifted upwards. Why? Because the steel, it is less than the balanced section. So if you see this strain profile, if the load is being further increased, what happens is that the variation of the strain in the concrete will be less, and the strain in the steel will be more. You can see a strain in the steel will be more, strain in the concrete will be less. As the further load is increased, proportionately strain in the steel, it will be more. So proportionately the strain in the steel will be higher compared to the strain in the steel will be lesser. So therefore what happens is that the steel is going to reach its maximum value before the strain in the concrete. So therefore what happens is that our steel is going to fail. First compared to the strain in the concrete. So therefore this type of section we can call it as under reinforced section. In the previous videos also we had seen what I mean by over reinforced, under reinforced and a balanced section. So actually what is happening now? So from this you will come to know why it is failing first. So if you see the strain diagram, so what happens is that the depth of the neutral axis, it will be shifted upwards. So if it is shifted upwards, you can see now the strain will be more in the steel, as well as strain in the steel concrete will be lesser. So further when the load is being increased, so more strain you are going to get in the steel compared to the strain in the concrete. Why? Because from this profile you will come to know. So therefore with further increase in the load, strain will be higher in the steel. So therefore this steel is going to fail first, or it is going to yield first compared to the concrete. So therefore this steel is going to fail first. So therefore we are going to have a tensile failure. So that type of section we can call it as a under reinforced section. Then next is, for example, over reinforced section. In over reinforced section what happens is that, now this is the depth of the neutral axis. So what happens is that if you are going to have more steel, then what happens is that neutral axis, it is going to shift towards this tensile part. So it is going to shift downwards. So now you can see now strain profile here, it will be lesser, it will be higher. So as the load is being further increased, if you see the profile, so strain in the steel will be lesser, but with slight increase in the load, strain in the concrete, it is going to increase largely. So therefore what happens, as the further load it is being increased, so strain in the concrete, it will be very larger. So therefore concrete, it is going to fail first compared to the steel section. So therefore this type of failure you can call it as a compression failure. Why? Because concrete is going to fail first. So which is a brittle failure. This is what we want to avoid. So this type of section we can call it as a over reinforced section, or this type of failure we can call it as a compression failure. So this is what it is being written in the words. You can pause the video and you can prepare notes of this. This is for a compression failure. For balance section, under reinforced section, and over reinforced section. As this is a compression failure, therefore this is a over reinforced section. Then next is at the end what we can summarize now. What we can summarize, if you see the formula, that is XU, depth of the neutral axis, if it is less than XU max, we can see here now. So this is nothing but XU and XU max. If the depth of the neutral axis, if it is less than XU max, so XU max is here and our depth of the neutral axis is here. If this value XU, if it is less than XU max, this depth of the neutral axis is here. If this value XU, if it is less than XU max, this type of failure we can call it as a under reinforced section. We can call it as under reinforced section. Similarly, if the depth of the neutral axis, if it is equal to the maximum depth of the neutral axis, then we can call it as the section as a balanced section. Then next is, if the depth of the neutral axis, if it is greater than XU max. So here you can see this strain profile. If you see this depth of the neutral axis, we have, this is the maximum depth of the neutral axis. This is XU max. If XU is greater, this is XU we have, this is XU max we have. So if XU is greater than XU max, then we are going to have over reinforced section. So that is what it is being avoided. Similarly, based on that itself, factored moment, if you calculate based on this concept itself, if you calculate moment, same thing we are going to have. For moment, if it is less than limiting moment, we can call it as a under reinforced section. If moment of a section that is equal to limiting moment, we can call it as a balanced section. If the moment, if it is greater than the limiting moment, then next what we have to do is that we cannot design it as a over reinforced section. Why? Because we are avoiding this type of sections. So therefore what we can do, we can redesign the section. So redesign means what happens that either we are going to increase the dimensions or we are going to go for a doubly reinforced beam. So till now what we have seen, it was for a singly reinforced section. So if moment, if it is greater than the limiting moment, what we have to do is that we have to redesign it as the limiting moment. What we have to do is that we have to redesign it as we have to redesign that section. That is, either we have to change the breadth or depth of the section, or we have to go for a doubly reinforced section. So we cannot go for over reinforced section. So this is avoided. Why? Because this is a compression failure. This is a brittle failure. Brittle failure means suddenly our structure is going to collapse, which may lead to the catastrophic failure of whole structure. So this has to be avoided. Then next is the maximum and minimum area of steel. So this also it is being given in the code, that is 26.5.1. So the minimum area of reinforcement what has to be provided, that is AST. What is the minimum area of steel that has to be provided? So that is being given by the formula, that is 0.85 into F of Y. With the minimum, this much steel has to be provided in the section. Now what is the maximum section or maximum reinforcement that has to be provided in the beam? So that is nothing but force percentage of the cross sectional area, or 0.04 BD. It is not 00, it is 0.04 BD. That means 4% of the cross sectional area. So this you have to remember, what is the minimum steel that has to be provided. So this much minimum steel has to be provided, and maximum is nothing but 4% of the cross sectional area. So you cannot increase beyond this. So this is the minimum and maximum reinforcement that has to be provided in the section. So let me show you now what all things we have covered. So this we have seen. Then next is 26.5.1 I think. So here they have given, you can see 26.5.1 I think. So here they have given, you can see 26.5.1, that is the requirement for the reinforcement for a structural members. This is regarding beams, tension reinforcement. What is the minimum reinforcement? the minimum area of the tension reinforcement shall not be less than that of this value, that is A by AS by BD is equal to 0.8 F of Y. So our area cannot be less than that, area of steel cannot be less than this. So this care has to be taken. So everything they have given what in by area, that is minimum area, B is nothing but breadth, D is nothing but depth, and F of I is nothing but the characteristic compressive strength. This is regarding the minimum reinforcement. Next comes is maximum reinforcement. Maximum reinforcement cannot exceed 0.04 D. That means it cannot increase, means you cannot provide more than 4% of the steel. So therefore these two care has to be taken while designing the beam of a singly reinforced section. Then next comes is here in this they have given, let me show you this annexure, what you can say, G. They have given, just now we have calculated moment of resistance for a rectangular and T section they have given. So just now we have seen for a rectangular section. So everything is being given just now, what all things you have done. So we have to calculate the depth of the neutral axis. How to calculate the depth of the neutral axis? That is XU by D, that is equal to 0.87 F of I into AST divided by 0.36 FCK into BD. So with the help of this formula we can calculate the maximum depth of the neutral axis. If the value of XU by D, if it is less than the limiting value, just now previous to this we have calculated the limiting values also. Calculate the moment by this formula, that is 0.87 F of I into AST into D into bracket of 1 minus of AST into F of I divided by BD FCK. This formula already we have seen. So directly in the codebook itself they have given, directly you can refer this and you can write the formula and you can calculate the moment. So if for example if XU by D, if it is equal to limiting moment or limiting value, so instead of this what you can say XU, you can use this XU max. So therefore it will be 0.36 XU max by D 1 minus 0.40 XU max by D into FCK BD square. This also we have seen. So for example if XU by D, if it is greater than the limiting value, then what happens is that we have to redesign the section. We have to redesign the section. Already this also we have seen. What all things you have seen just now, all those things, everything is being given in the codebook itself. So how these formulas they are coming, that we have seen in the video, right? So this is regarding the singly reinforced section. If you want to go for doubly reinforced section, that is for compression reinforcement, again that formulas they have given. So this we will try to cover it in the next video.